Okay, maybe that's not bad.
Okay, good morning. Wow, it's Friday. All right, so the cool thing about today is we're going to combine the vibrational spectroscopy that we did a while back with the rotational spectroscopy we did last time. So in the gas phase, a molecule can have a transition in its vibration and a transition in its rotation. Now, that would be a disaster except for selection rules. So that's just sort of illustrates the importance of selection rules, because the spectra for gas phase row vibration, or at least for a symmetric molecule, are pretty easy to interpret. And so this is a good example of why symmetry really comes to the rescue for us. So what we have is the vibrational potential that you see here in blue, and then on each of those vibrational levels we have the rotational lines. And so one of the things I do want to point out is that again, by convention, the first spectra that they interpreted were emission spectra. And so, you know, you typically label something first as prime and maybe a second thing as a double prime, right? So for their case, the original case, emission spectra, the first state was the upper state and the second state was the ground state. Well, they started labeling it that way with primes and double primes. And now for absorption, we just forget about what was first or last. We just label the lower state as the double prime state and the upper state as the prime. So that's really important, because you're going to have a lab related to this too. And if you don't understand that the quantum numbers that are double prime are the lower state ones, and the quantum numbers that are single prime are the upper state ones, then it's going to be a real problem. Okay, so that's a foundational principle, at least for the next couple of weeks, certainly in next week's exam, and then also in the lab that's in 2 weeks. So we're doing quite a bit of stuff today related to the lab that's going to be coming up, not next week, but the next. And this prime, double prime thing is something that if you don't pick up on that, you're definitely going to be confused trying to do those labs. Okay. Now, this is the single beam spectrum, infrared spectrum in air. And so we have, in the infrared spectrum, we have the stretching region. So for the small atoms, like for hydrogen, nitrogen, hydrogen, nitrogen bonds, carbon, hydrogen bonds, oxygen, hydrogen bonds. Those are up in this upper region. And then down here we have the angle bending regions and the heavy atom stretches, like the carbon-chlorine stretches, the carbon-fluorine stretches, and so on, carbon-carbon stretches. But typically we have the spectrum sort of divided in half. And you notice from organic, right? We call this up here, or down here, we call this the fingerprint region. Because when you look at your fingerprint, there's really no rhyme or reason to it. It's just complex enough to isolate you from everybody else. And that's kind of the way we've treated the lower part of the infrared spectrum, is that we really can't know in organic why this peak is here and all these combinations of peaks, but it's enough to separate this molecule from that molecule. Well, in this course, we're actually interpreting quite a bit about what's going on in this region, like we did with that acetonitrile spectrum. We went through every peak and said, this is the bend, this is a different kind of bend, this is a deformation of the methyl group. So we can understand what's going on in the fingerprint region, but it's pretty complex. And what I do in terms of trying to understand the fingerprint region is I just do a Gaussian calculation and calculate the vibrational frequencies, and then I animate every one of them. And so I can see what that peak is. It's a twist or a turn or a deformation of something. So you can understand the fingerprint region, but it's all of those angle bends in the molecule. These are the CO2 vibrations, and these are the water vibrations. Again, this is air, so we have moist air, we have CO2 and air. And in this right here, those little bumps, notice they don't show real fine lines. It's because those are fingerprints on the windows of my spectrometer. Okay, so it's very sensitive. I mean, that's like maybe one fingerprint will give you that much signal. So that's just, some contamination there. Over here, if we zoom in on that carbon dioxide signal, we see that there's these little wiggles here that are equally spaced. And so we're looking at this area here, and that's the rotational lines on top of this vibration. And then this is a sharp peak here, which we'll understand what that means, and then we have all these other little wiggles. Those are real signals. Those are different rotational quantum transitions on top of a vibrational transition. So this is in the infrared, not in the microwave. The pure rotational spectrum would be down in the microwave, really low energy, 0.1 wave number or something like that. And we're at 500, 600 wave numbers. So this is a vibrational transition and some rotational transitions on top of that. And that is motion perpendicular to the symmetry axis. So if you look at the arrows here, this is the bending motion of that linear molecule. So it's kind of bending in half. Okay. And then up here we have the parallel band. We still have this P and R branch, which we'll explain today. And this is a vibration parallel to the symmetry axis. So this is the carbon-oxygen stretch. It's the asymmetric stretch. So if my head is the carbon and my hands are the oxygens, it's this one. So it's stretching like this. And that sets up a dipole moment that changes with vibration. And so that's why it's infrared active. The symmetric stretch, there's no change to the dipole moment, and so that's in the Raman spectrum, not in the infrared. So we don't see the symmetric stretch, but we do see the asymmetric stretch. The bend over here on the right, the perpendicular band, that's this. That's the oxygen and the carbons bending. And the reason there's a Q branch is because you can get kind of a pseudo rotation in the vibrational motion. It could be going this way too. So if it's bending this way and that way, they can combine to kind of create this pseudo rotation. This is a bending, this is a vibration, but it looks like a rotation. So it's bent this way, and then it's bent that way, then it's bent down, then it's bent to the back. And it looks like the carbon is spinning inside the two oxygens. So that's where, in those situations, you can have a Q branch. Now let's unpack what P, Q, and R branches are. This is so important that we have prepared your mind to understand if I got the energy levels, I can understand the spectral lines. So once again, we're thinking about, show me the energy level diagram, and then that tells me where the spectral lines will be. The longer arrows have a shorter wavelength. The shorter arrows have a longer wavelength. So from this, we have this region we're zooming in on, the first two vibrational states, and we're going to have the energy level diagram up here. So we have the rotational energy levels. That's the energy for the rotational levels. And so we have the ground state vibrational level and the ground state rotational level. So we're drawing these lines here. Notice where all these down at the bottom are V equals 0. So the ground vibrational state. And then we have J equals 0, J equals 1, J equals 2, and J equals 3. So just for space, that's all we're drawing. But it goes on up J to 150. I mean, we can have, almost an unlimited number of rotational lines. They go up as J squared, so they're not equally spaced. Do you see that? They're not equally spaced. Because the energy level for J is B, the rotational constant, times J plus 1. So it's a J squared plus a J. So it goes up as J squared, just kind of like our particle in a box did. So that's the ground vibrational state and the lower rotational states, the double primes. Now, the upper vibrational state, we put in a V. So here's our vibrational quantum number here. This is V, okay? We put in a 1 here, okay? And then we have the vibrational frequency for this motion. And so we have 1 plus a half, so 1.5 times the vibrational frequency. And that gives us our energy for our upper vibrational state. So that's the V equals 1. And then on top of that, we have the rotational levels too. So we have the upper rotational levels, J equals 0, J equals 1, J equals 2, J equals 3. So if I were to write the quantum numbers here for that state, it would be V equals 1, comma, J. I'll go ahead and put primes on those. V prime equals 1, J prime equals 0. And down here, I have V double prime equals 0, comma, J double prime equals 0. So you see every energy level has an address. It has a set of quantum numbers. So that's the energy level diagram for rotation and vibration. Now we'll look at the selection rules that we get from symmetry, and then we'll start to make the spectrum. But is there anything I need to clarify right now? Okay. So the selection rules are delta V equals plus or minus 1. So we're just going to go absorption. So we're going to go from V equals 0 to V equals 1. So that's our vibrational transition. And then our delta J values can change by 0 or plus or minus 1. And so we'll do all of those three cases individually. So let's start with the delta J equals 0. So that means we're going from 0 to 1 in vibration, and we're going from 0 to 0 in rotation, or 1 to 1 in rotation, or 2 to 2. You see, the J's aren't changing. So this is the 0 to 0 rotational change on top of the vibrational change. And I've color-coded these arrows so that red light is a lower wavelength than green, which is a longer wavelength than blue. So blue is the shortest wavelength or the highest energy or the longest arrow in the energy level diagram. So it's color-coded correctly. So let's start in the middle with a green light. Even though this is in the infrared, it's not in the visible, but I'm just using the colors to give you an idea of which are the higher energy transitions and which are the lower energy transitions. So we're right here in the middle. And all of these, because the rotational equation is not, the rotational constant's not that different with vibrational excitation. These all fall right on top of each other. So the difference between these levels is just that vibrational difference because there's no change in J. So that's all of those are going to fall under one peak in the spectrum, and that's called the Q branch. We'll label the branches in a minute. Okay. So those are the delta J equals 0 lines. I'll go ahead and circle that. And circle all of these. Okay. So those are all delta J equals 0. And you can look at the energy level diagram and see that. It's 0 to 0, 1 to 1, 2 to 2, 3 to 3. All right, let's do now the plus 1, delta J plus 1. So now it's going from 0 to plus 1 in the J and 0 to 1 in the vibration. So we always have these two transitions because it's RO-VIBRATIOnal spectroscopy. We have a rotational change and a vibrational change. So that's 0 to 1 in J, 0 to 1 in V. Then we have 1 to 2, right? All of these on the right-hand side are going to be, like a delta J plus 1. So it's 0 to 1, and the next one is 1 to 2, and the next one is 2 to 3. Pretty straightforward, right? We're just going through the selection rules. So these are all of the plus 1 J's. So I'm going to circle those. And that's the plus of the plus 1. Now those, notice how the arrows are not the same length this time. See how close the 0 to 1 levels are? And so this kind of greenish blue one is this length, but this one starts a little bit higher, but notice this gap is bigger right here. And so this light blue arrow is longer. And so it's going to show up at a higher frequency or a shorter wavelength. Okay. And so this kind of teal looking one shows up there, the light blue one there, and the dark blue one there. So these are going to be separated in the spectrum. And so we can go to the spectrum and we can see the individual rotational transitions for the delta J plus 1. And then now let's do the minus 1. So then we can't start at 0 because we would have to go to negative J. And there are no negative quantum numbers. Okay, so we have, in this case, going from 1, starting in the first rotational level and going down to 0, so that's a minus 1. Starting in 1 and going down to, starting at 2 and going down to 1, or starting in 3 and going down to 2. Notice also that these gaps are not the same because the energy levels go up as J squared. And so these arrows get progressively shorter. And because they get progressively shorter, they show up at lower frequencies. And so the yellow one would be here, the orange one, and the red one. So this is the full interpretation of RO-VIBRATIOnal spectroscopy. You have the energy level diagram on top and the spectral lines down below. And because these separate themselves into groupings on the experimental spectra, we call them these labels. We labeled them as branches on a tree. Like you've got a tree and then the twigs come off of the branches. And so these little lines you can think of as twigs. And so we have a P branch with lots of little twigs, and we have the R branch with lots of little twigs. And the Q branch, they all fall down right on top of each other. So the Q branch is right in the middle, and the R branch. So these alphabetical order matches increasing wave number. So as they go up in energy, the lowest energy ones are the P branches, then you have the Q branch and then the R. So PQR in increasing energy alphabetical order. So it's always easy to remember that. What can I clarify about this? Okay. We'll actually see experimental spectra today that we can identify these branches on. Well, we could earlier with that CO2 spectrum. Okay, so this is just showing you some of the equations. This RO-VIBRATIONal IR spectroscopy is just, it's the sum of both the vibrational energy here. The total energy is the sum of all the individual energy components. And so we have the vibrational energy here, and we have the rotational energy here. Now this is missing our anharmonicity and centrifugal distortion, which will be in your lab, but we'll see those equations in a minute. So here are the combined selection rules, plus or minus 1 in V, 0 and plus or minus 1 in J. And here are the transition equations. So these are the equations that we have for those transitions. So what do I mean by the transitions? That's these things down here. The spectral lines are the transitions. And when we come up with the transition equations, they tell us what the locations of the peaks are. So I'm just reviewing a little bit. So we get to these transition equations. These are the vibrational frequencies. So this is the vibrational, the frequency in the spectrum for the P branch lines. And so it's the vibrational frequency and the rotational piece. For the Q branch, since there's no change in the rotational constant, no change in the rotational levels, we don't have any rotational information in the Q branch. So it's just the vibrational frequency. So that tells you the Q branch will be right on the vibrational frequency. So if you want to know what the vibrational frequency for that transition in CO2, just find that Q branch, and that's your vibrational frequency. The P branch lines, notice the rotational lines are less than the vibrational frequency. So they'll go off to low wave number side, that's the P branch, and then the R branch goes up in J. So this is the rotational piece. This is the vibrational piece. And there's a little offset. It jumps over 2B, and then it starts going higher and higher in vibrational frequency, higher and higher in wave number with each successive J value. So these are the transition equations for the P, Q, and R branches. Notice that as I go up in J value, from J equals 0 to J equals 1 to J equals 2, I get another unit of the rotational constant times 2. So the spacing between those lines is 2 times the rotational constant. So that's great because I can get the rotational constant from the spectrum by taking differences in those peaks. And the rotational constant contains my bond lengths and bond angles. So we have this 0 to 1 transition for the R branch. Then the next, and it's 2B over, okay? Then the 1 to 2 branch transition line is another 2B unit over, and then the 2 to 3 is another unit of 2B over. So we can use these spectral lines to determine what the rotational constant is. Noticing the P branch is subtracting 2B for each of those, and so that goes from the vibrational frequency down 2B. The next one goes another unit of 2B, and then the third one is another unit. So again, in all of these lines, the separation in absorption spectroscopy and emission in the infrared is 2 times the rotational constant. Let's look at Raman now, since that's another technique we could use. If we do Raman on the gas phase, we could see rovibrational transitions. But now we have this scattering, this what do I want to say, this inelastic scattering, and what we're going to be drawing, instead of drawing both photons, we're just going to draw the up arrows. We're looking at the transitions that occur here. Okay, so it looks like absorption, but it's still Raman scattering. I'm just showing you the transitions that occur. We have different selection rules, and so now the J values are plus or minus 2. Okay. And 0. So we still have Q branches. So there's our 4 Q branch lines, and they show up as one spectral line. But then now we're going from J equals 0 up to 2. So we're going by plus 2. And then we're starting at J equals 1 and we're going up to 3. Well, because I've only included 4 rotational levels, I can't draw any more on my energy level diagram. But there are lots more, because there are lots more rotational levels. So those would show up here and here. Notice the spacing is quite a bit different here, because we're jumping by much more. So we have quite a bit of difference, more difference than we had in the absorption spectrum, because our delta J's are plus 2 instead of plus 1. Now for the minus 2's, we're starting in 2 and going down to 0. We're starting in 3 and going down to 1. We can't go any lower than that. We can't start at 1 or 0, because we'd have to go to minus 1 or minus 0. And so we have those spectral lines here. So the take-home lesson here is Raman, the branch lines are spread further apart, because we have delta J plus or minus 2. And we can't call this a P branch or an R branch, because a P branch is delta J minus 1 and an R branch is delta J plus 1. So we have to give this a different label. And so we call this O. So it's below P. So we have O, P, Q, R, and S. So Q is the same, but S now is the delta J plus 2. So if you're dealing in Raman spectroscopy, you have O, Q, and S lines. But if you're dealing with just absorption in the infrared, you have P, Q, and R lines. P, Q, and R for the absorption, O, Q, and S for Raman. So here are the transition equations for those. We have those selection rules. We can take those energy equations and put in delta J plus or minus 2 and 0, and we get the O lines, the Q lines, and the S lines. And notice now we have a bigger spacing right here, this 4B. So instead of 2B, the O lines drop by 4B, and the S branch lines grow in frequency by 4B. So in our spectrum, we would have that O, Q, and S lines. And then we have the first rotational line. So the 0 to 2 transition for the S branch. I put in 0 for J here. And so this piece is canceled out, but I still have this 6B. So it's going to be shifted over by 6 times the rotational constant. And then for the 1 to 3 transition, I put a 1 in for this. Put a 1 in there, and so it's 1 times 4B plus the 6B, so that moves me over to 10B, but the difference between that is 4. 10 minus 6 is 4. So it's going up by 4B. If I put in the 2 to 4 transition, then I'm going to move over another unit of 4B. So every increase in J value moves me over another unit of 4B. So I can still get the rotational constant value from Raman spectra, only I have to know that it's a spacing of 4B, not a spacing of 2. And so for the 0 to 2 transition in the O branch, I'm subtracting 6. Where's that 6 come from? Well, I put in a 2 here. We're putting the initial states in here. And so 2 times 4 is 8. So minus 8 plus 2. And so the difference is 6. So I'm dropping by 6B. And then I put in a 3 here. 3 times 4 is 12, minus 2 is 10, so I drop by 10, which then the difference between 6 and 10 is 4. So I'm dropping 4B with every O branch line. And those are the branches for Raman spectroscopy. And the key is we need to know these differences so that if we're given a pair of spectral lines, we can determine the B value, and then we can determine the bond length. it's so important to know the difference between Raman and IR for these things, because in all other cases you can use units to tell if you're on the right track. But in this case you can't, because you just have to know the spacing of the lines. There's no unit associated with that number 4 or that number 2. And so you wouldn't know if you're wrong, and you would have incorrect results. And so this is something you just have to know. Raman spectra, the spacing in the lines is 4b. Infrared spectra, the spacing in the lines is 2b. And so that leads us to this classic question. Hamlet ponders, to be or not to be? That is the question. And DW answers, if it's absorption, it's 2b, and if it's Raman, it's 4b. Okay, so I had to, you know. All right, so now I'm going to pause. I'm going to stop that video. That's RO-VIBRATIONal spectroscopy. Okay, that's the theory behind it. I'm going to stop the video and start it again, because this is related to your lab in 2 weeks. And so I'm going to put both these videos on the lecture part of week, whatever we're in, so that you can watch them. But then I'm going to copy that video into the week where you're doing the lab. And so when you're doing the lab, this second half of the lecture will be in the lab part of the course. So you don't have to kind of go back and find it. Okay? Okay, so let me escape here.